No, you should be good.
I was already green. So it's very confusing. Okay, sorry. And okay, so yeah, we said these guys are the enemies to doing gluing. And this guy, okay, this is the solution to the wave equation. This is basically the radius or the conformal factor we define for the sections. This is the transversal derivative. This is the round metric. And this guy exists if and only if certain conditions are satisfied on your null hypersurface. And basically, the theta thing has to do with the kernel of this operator here. Not only you need to have kernel for every section, but you want this kernel somehow to be related. Okay, and specifically, you want every section to have a kernel of this form. 1 over times the conformal, 1 over the conformal factor times a function that is independent of your sphere. So the kernel as the kernel itself changes. This guy changes, but if you take 3 times the kernel, it shouldn't change. All right, that's the result. And these are 3, as we said the last time, examples where you have such conservation law, so you don't have always gluing. First of all, for any standard null hypersurface in Minkowski, at null infinity, along null infinity, rescaled versions of the previous ones for asymptotically flat spacetimes, and for black holes. So whether that kernel has that property of the adjoint is decided by this constant here for stationary black holes, and that constant, if it's non-zero, then you don't have conservation laws. You can prove that. And if the constant is 0, then you have conservation laws. Again, you can prove it. And that constant is the surface gravity that decides whether your black hole is extremal or not. So in the extremal case, we have a conservation law that's of this form. That's extremal. That is extremal as a notion. That's extremal care. All right, let's spend a few minutes on seeing a few applications of these integrals, okay, over the sections, like the abstractions to gluing. When we want to study the dynamics of black holes, we need to be familiar with a few properties of the near horizon geometry. There is this global redshift test effect, that it is exactly what you see in the picture. You don't have to read the text. You have an observer crossing the horizon. You have an observer staying always in the domain of outer communication. And as the observer emits signals, the signals get redshifted. That's an effect that is present in all kinds of black holes, extremal or sub-extremal. But if you try to localize this, and instead of having this guy being always in the domain of dependence, instead of having this, you have this guy being close to A. So now you localize it around A. Then the picture is very different, because in the sub-extremal case, you still have that redshift. In the extremal case, your redshift has degenerated. Okay, signals are not anymore redshifted along the horizon. And the reason for this is always, like the reason for these two different cases is this constant here, kappa. Okay. Moreover, there is another geometric interpretation somehow between the two cases. So this is the sub-extremal case. This is the extremal case. In the extremal case, if you start with null cones very close to the horizon and you shoot them out, like if you start with outgoing null cones, then you see that as time progresses, then these cones diverge from each other locally to the horizon, but they diverge. Whereas this divergence does not really occur in the extremal case. So this is consistent with dispersion. Your geodesics, if your characteristics diverge, is consistent with dispersion. This thing is consistent with not that much dispersion. And another effect that one needs to be familiar with when studying, again, the dynamics of black holes is the photon sphere, which means that you have null geodesics, which neither cross the horizon nor go to infinity. So they stay always in the domain of outer communications. Okay, and such geodesics, of course, for example, do not exist in Minkowski, right? All geodesics have to go to infinity. In the black hole case, you have such geodesics, and the issue with them is that energy will be following these geodesics for a very long time. So there will be concentration of energy in the bounded region in the domain of outer communications. All right, so given these properties, one can ask this problem. Given an initial slice, which you can assume that it crosses the horizon and it terminates at either at null infinity or at space-like infinity. And given initial data for the wave equation on this slice, how does the arising solution behave in the future? And you can ask this problem globally, both in the interior and the exterior. We care about the exterior here. All right, so the ultimate goal for this problem is to derive asymptotics in time, okay? Asymptotics meaning how your scalar field behaves along the event horizon, towards time-like infinity in the bounded region, and along null infinity towards time-like infinity always. Right? You want to derive asymptotics. Asymptotics are slightly more important than just decay, because when you have decay, you know that your thing is small, but asymptotics give you also lower bounds. They tell you that you are not too small. And so when you have asymptotics, you have upper bounds, which is good for stability, but you also have lower bounds, which is good for instability. So we want to derive asymptotics, not just decay. The most important result in this area is, of course, the work of Yakov, Michalis, and Igor for decay in subextremal care. Now, let's just refine these decay results and see how we can derive asymptotics, okay? So instead of saying that the solution is bounded by this, we will say the solution is actually this term plus something smaller. That's the refinement. And I explained to you the reason why we want to do this. And what I want to convince you is that when you go from decay to asymptotics, what you actually need is these conserved integrals that we have as abstractions to characteristic gluing. And that's a relation between the two theories, the dynamics and the gluing. All right, anyway, let's start with the simplest case, which is Schwarzschild. We will consider the dynamics, like the asymptotics of your scalar field along the horizon, away from the horizon by bounded region, and of the radiation field at long null infinity. For the general solution, you are expecting 1/t⁵ decay. That's consistent with Price's law. And that's what we have, exactly 1/t⁵ decay. But we even have, for the precise asymptotic term, we have the exact coefficient that this is behaving. This is this term plus something faster. And what is interesting is that along the horizon and away from the horizon, the coefficient is the same. And what is slightly more interesting is that if you look at the asymptotics of the radiation field, they decay a little bit slower, but the coefficient is actually proportional to these coefficients. And here, if you go a little bit further, instead of going 1/3, you go to log t over 1/3, and the coefficient again is this guy. Okay, so you have one number, this is a number, that determines your asymptotics everywhere. Now, this number, you can write down explicitly very easily in terms of the initial data, in terms of whatever you had here. Because whatever you have here is actually what determines everything, right? So for Schwarzschild, that's this number. This number is exactly this guy here. It is the integral of your normal derivative initially, plus an integral over your over the initial section of the horizon. So it's very simple. Okay, so far it has nothing to do with characteristic gluing and conserved charges. but the conserved charges start making their appearance here. So let's try to understand what this constant is from a more global point of view, not just from the point of view of initial data, but a little bit more globally. Let's see what it is. So you remember that I told you that this is a domain of outer communication. This is the event horizon. This is null infinity. This is time-like infinity. We said that for asymptotic flat spacetimes, there is a conservation law along the null infinity. Right, it's that guy there. This is the same conservation law that acts as an obstruction to gluing along null infinity. All right. Now, if you assume that your initial data are, say, compactly supported, so you only see a local perturbation on the horizon and everything here is 0, then these results here still work, all right, even for compactly supported initial data. But if your data are compactly supported, then that means that there is a triangle somewhere here where your solution is trivial. And if your solution is trivial, that means here whatever expression you write will be 0. So whatever expression is conserved along the horizon will be 0, because it will be 0 in a portion of null infinity, because you assume compactly support of the initial data. So in other words, the Newman-Penrose constant associated to your solution to the wave equation will be 0 if the initial data for that solution to the wave equation are compactly supported. All right, so if you have a quantity that it is 0, it's good to know that it's conserved, but it's not good enough to give you lower bounds. It's maybe good for upper bounds, but not for lower bounds. 0 can never give you that something is bigger than something else. So here is the first main observation, is that, okay, the constant that determines your global asymptotics is not actually the Newman-Penrose constant at infinity of your scalar field, but it is the Newman-Penrose constant of the scalar field that you obtain after removing from it a time derivative. If you add a time derivative, then your scalar field is still compactly supported. If you remove a time derivative, then your scalar field is not anymore compactly supported, because removing one time derivative is non-local operator, right? Basically, this is the time integral. So you integrate over all times. Of course, you will see points where your scalar field will be non-zero here. So this constant here that is given by this expression initially and appears everywhere in the asymptotics of the scalar field is simply the conserved charge of the time integral of C. All right, and that's the first instance where the conserved charges make their appearance in the dynamics of your scalar field. Okay, it's just that instead of considering the scalar field, the charge, the conserved charge of C itself, you have to remove one time derivative. Now, if you have your time integral, then you use this expression for the time integral, the definition of Newman-Penrose constant, you get this constant here. If you don't want to compute your time integral, then there is another way, apart from this, to determine this constant. Instead of looking initially, you can look at your scalar field along the null infinity. Okay, and all you have to do is integrate the radiation field. If you integrate the radiation field along all of null infinity to the future of your initial data, then what you get is this constant, the same constant here that gives you these results. So the same constant that again is related to a conserved charge at null infinity is what you need to know in order to determine your asymptotics in the asymptotic region and even in the close to the horizon region. Let's continue a little bit more. Let's go away from pure vacuum and go to Einstein-Maxwell, in which case the simplest black holes are the sub-extremal as the Nordstrom. same problem, study in the exterior region the wave equation. Let's consider the asymptotics. And what you observe that the asymptotics are exactly the same, okay, as in Schwarzschild. -8, -8, -2, -8, -8, -2, exactly the same asymptotics. The charge does not make any appearance here explicitly. For the full subextremal, this is not for small charge, it's for the full subextremal region. All right, so one could say, okay, since this is true for all subextremal cases, maybe you can take the limit as your charge tends to the extremal value. But that is not the case, as we will see, because the error terms, the terms that are slower than this in the asymptotics, actually grow as you tend to the extremal case. Even though the top order term in the asymptotics is independent of the charge, the next terms are depending on the charge. So it could be the case that these asymptotics get extended to the extremal case, but it's not necessarily the case. So why one would want to study the extremal case? Like I told you also yesterday that the extremal case will play an important role in today's lecture. There are both theoretical and practical reasons. Theoretical is because these black holes act as geometric minimizers, and they are actually, due to recent work of Christoph and Ryan, these two guys, they actually play a quite important role in gravitational collapse when you go from dispersion to collapse. Anyway, and there is also maybe some astrophysical literature making them relevant. In any case, these are the asymptotics in the subextremal case. You see the decay rates are -3, -3. These are the asymptotics in the extremal case, -1, -2, -2. So these decay rates are completely different from the subextremal case. You have much slower decay. And moreover, the coefficient now is different. Instead of having that I guy, which was this conserved charge from the time integral from infinity, you now have an H guy. And when you look at the radiation field, you have both the H, the new guy, plus the previous one, this time integral guy. So what is this new coefficient now that gives us these new asymptotics, which are much slower? Well, it is exactly the conserved charge at the horizon. Okay, we said that if k is 0, kappa is 0, then you have a conserved charge at the horizon. If kappa is non-zero, which happens in the subextremal case, there is no conserved charge here. There is only conserved charge here. So that only conserved charge here is the one that was dominating everything, everywhere. Now that you have a conserved charge here, then your asymptotics here are dominated by this guy, and your asymptotics here are dominated by this guy plus this guy. That's what this is telling you. Okay. Now this new conserved charge at the horizon, at your new horizon, is the one that's now dominating the asymptotics, and in fact, it's even bringing you much lower decay. All right, so psi decays everywhere, much lower, but at least it decays. You see, these are all inverse powers of time. But if you look at transversal derivatives, they cannot decay precisely because they are conserved along the horizon. And actually, if you take second order transversal derivatives, these grow. Okay, so you have growth, which is a sign of instability along the horizon. Away from the horizon, all derivatives and all derivatives of psi actually decay. So this growth is only on the horizon. This is what we call the horizon stability of extremal black holes, and it has been extended by various people. My student Marios has extended this instability for the linearized gravity system, and more recently there have been extensions by Angelopoulos and Ryan in the fully nonlinear regime within spherical symmetry, but still this instability survives rigorously the nonlinear theory, in the nonlinear theory. Now, I want to tell you something, since I maybe have time, I don't know. Let's very quickly see a few more aspects of this conserved charge. Like we said, the conserved charge here actually is giving you an instability at the horizon. And it makes its appearance, in the asymptotics close to the horizon, but even at the radiation field at infinity. Let's go a little bit further. Let's define here the limit of the radiation field in time. Okay, that's you take the radiation field and you take its limit here. That's what we call S0. And then what you do is you take that S0 and more. So that's just a limit here. This is just a limit here. And moreover, you add to it the integral of the radiation field, which is this guy. And of course, you integrate not just in time, but you also in angles. You integrate overall null infinity. So if you take that expression, then that expression that you can completely determine given the radiation field and nothing else. So if you know things at infinity over all angles, then you can compute this guy. And what is interesting is that this guy has this continuous property when you go from subextremal black holes to extremal black holes. Generically, in the subextremal case, this guy is always 0 for all scalar fields generically. And actually, no, it's for all scalar fields, it's always 0, not generically, it's always 0. But in the extremal case, this guy is generically not 0. So if you have a perturbation of a Rising-Nordstrom space-time, and you know its radiation field at infinity, and nothing else, then you can compute this guy, because this is purely radiation field guy. You compute this guy. And if you get that its value is non-zero, then you can conclude that, in fact, you are a perturbation, or your field is a perturbation of extremal Rising-Nordstrom. So you can separate between subextremal black holes and extremal black holes by only looking at the radiation field. Okay, just your asymptotics at infinity are enough and nothing else to give you to separate subextremality from extremality. Yeah. This is for it's in the world of compactly supported data, because they don't have to be compactly supported. You can have some strong decay, but not too slow decay, because then you have different decay rates. All right, so if you have too slowly decaying rates, then you can have logarithmic corrections as your top order terms. It's different. But this is in the world of local perturbations of the horizon, which basically means compactly supported. And one more comment I want to make in this direction, how knowing things at infinity can tell you something about globally about your space-time. Like knowing your scalar field at infinity can tell you your geometry globally, what kind of geometry it is. Here is what I want to say. So this number that you computed before was a number that you needed to integrate over all angles of null infinity. What if you just want to focus on one angle? Like you don't want to know your universe in all directions, but only in one direction. Then you can consider this expression here. This is now this guy here is the radiation field, not the, this is like ARPC. And again, you take the limit of this, but now you see no integral. All right, there are no integrals. It's only limits in time, no integrals over angles. It's just that these limits are slightly more singular in the sense that they have some logarithmic coefficients. But this, if you know your radiation field, then you take these limits along null infinity and you determine this constant. These constants have exactly the same behavior. Okay, if it is always 0 in the subextremal world, and it's generically non-zero in the extremal world. So even if you know your scalar, if you know you have a perturbation of extremal black holes, of a Rising-Nordstrom black hole, how can we draw this? So let's say this is the black hole, this is null infinity, all right? And you only know your radiation field at a very specific direction of null infinity. You don't know it here, you don't know it here. Let's say you only know it here. That, just knowing along one null generator of null infinity, your radiation field is enough, generically, to tell you whether your full space-time is extremal or subextremal. Okay, that's what this is telling you. It's like a localized way to understand, to separate extremality from some extremality. Now, why am I saying these things? because both of these constants in the sub-extremal case are 0. In the extremal case, both of them are actually the horizon charge. So the horizon charge is a constant that is defined exactly the horizon in the extremal case, but you have the ability to read it from the radiation field along one null generator of null infinity. And in that sense, we can say that extremal black holes admit classical here that are externally measurable, right? You are null infinity, you compute something, and what you compute is actually the hair of extremal black holes. All right, so that's what I want to say. That's like the main result that connects these conserved charges with your asymptotics, your dynamics of black holes. Very, very quickly, let me just say a little bit more about the dynamics of black holes. What I talked about is extremal Rieser-Nordstrom. Our friend Dejan has more improved results for extremal Kerr, where the asymptotics are actually worse. Instead of having 1 over t decay, he proved 1 over root t decay. And even the first order derivative now grows. So that's a result where you don't have any precise. This is for non-azimuthal frequencies, non-asymmetric frequencies, I mean, sorry. And that's a result that you have very strong instability without the presence of a conserved charge. So it's not that always the conserved charge is what saves you. You can have bad behavior without the conserved charge. Because the conserved charge in the extremal case concerns the frequency where m equal to 0. In which case you have results similar to Rieser-Nordstrom, extremal Rieser-Nordstrom. In the extremal case where the azimuthal frequency is non-zero, that conserved charge, are orthogonal, but still you have an amplified instability. And you even get the asymptotics along null infinity, and you can compare what happens in the extremal and the sub-extremal case. But anyway, that's something related to what Yakov asked me. What if your data are not compactly supported? In fact, what if you start from data not from Cauchy hypersurface like I showed you before, not from such a guy, but if this is the event horizon, this is null infinity. Instead of doing data in the future of like that, you can start with data which are considered to be more physically relevant, which are data from past null infinity. All right, you can put data here and here. And then once you solve this data and you get here, then here you will not have compact support anymore. And in fact, these data here are much stronger than the data that I assumed previously. And for this red data, your behavior is very different, okay? Already, like instead of having, this is for Schwarzschild, instead of having 1 over t to the 3, you have a log term. Oh my God, log should be upstairs, not downstairs. Sorry about this. It's a log decay, not log improvement. Sorry. Anyway, so if your data are somehow not very slowly decaying, then you might have logarithms slowing you down. No, because this is just for like at least these results only for the wave equation, so there are not really constraints here. Of course, he has similar results for the scalar field in spherical symmetry, but the reason you get something much stronger here is even if you solve in this region, something that decays nicely here, along in the neighborhood of time of space like infinity, it's already amplified here. So it's not really a result along past null infinity. It's a result in this slab. And this is the result that I also mentioned previously, a result of Yannis and his collaborators, Christopher Ian, where again, they show that you have a type of instability, like your scalar field and some curvature components, not decay and actually even blow up in a neighborhood of extremal Rieser-Nordstrom in this system. Okay, spherical symmetric Einstein-Maxwell chargeless scalar field. All right, so we're done with the linear theory. Now let's pass to the nonlinear theory, which is of course not true because everything I will say is actually relying on the linear theory. But anyway, so now let's go back to the characteristic gluing problem. We consider two spheres, and on each of these two spheres, we consider all these functions or tensors. We consider the null apse omega, we consider the conformal factor, we consider the conformal metric, we consider the second fundamental form, we consider the torsion, and here derivatives of metrics and curvature components. So we prescribe all these guys, these geometric guys, here and here. And we want to know whether there is a null hypersurface, where there is a metric, first of all, which admits, for which there is a surface connecting those two sections, and for which that surface is a null hypersurface. And along this null hypersurface, you solve the constraint equations for the Einstein equations. And when you restrict that metric on both of these two spheres, you recover this data. Yeah, I want to remind you something very important, that the characteristic initial value problem for the Einstein equations is a little bit different compared to the Riemannian case, because in the characteristic case, you are allowed to freely specify the conformal geometry of your null hypersurface. Okay, in the space-like case, you have to specify the first and the second fundamental form, but you have to make sure they solve the constraint equations. Here, this guy, the conformal geometry of every section, is freely specifiable. And also what's freely specifiable is this omega, which basically amounts to deciding what kind of sections you will use to connect this one to this one. Given a null hypersurface, as we said yesterday, there are infinitely many ways, to go from here to here. You can change your sections along the way. And this basically omega is a way to specify the sections. And once you specify your sections, you can freely specify the conformal geometry. So given geometric data here and here, our problem is to find an omega and conformal geometry for each section that we have to construct. But anyway, for each section, we have to find these guys there, this couple there. So that when you solve the constraint equations, first of all, you solve the constraint equations, and then you recover this data at both spheres. These are the constraint equations. Okay, so that's the equation for the full metric, for the conformal factor, the second fundamental form, etc. And actually have a slide from the paper, so you can see all the equations. These are in the transversal direction, but okay, this is equations along the hypersurface. All right. And this is the problem, as I said, given two spheres, find the hypersurface, which is basically a family of spheres connecting the two spheres, such that along this hypersurface, you solve the constraint equations and you recover at both boundaries your prescribed data. This is what we can freely specify, and then we solve for everything else. Now, if you remember, for the wave equation, the only obstruction to constructing such a thing is conservation laws for the wave equation. For the null constraint equations, you have way more significant obstructions, one of which is already the Resadur equation, right? Which is a monotonicity, not a conservation law, it's a monotonicity obstruction. But on top of that monotonicity obstruction from the Resadur equation, which I think I misspelled, you actually have obstructions coming from the linearized null constraint equations. And actually, there are infinitely many such obstructions, all of which take the form of a conservation law. And this is when you study this problem close to Minkowski, all right, which means you're close to Minkowski, then you can linearize around Minkowski, and then the linearized constraint equations have an infinite class of conservation laws. And these are, again, again, let's, for simplicity, not for simplicity, but I mean, as a first step, let's assume that everything you try to do is close to Minkowski. So this is a sphere of radius 1, of almost radius 1, with all the data close to the data of a sphere of radius 1 Minkowski. This is a sphere of almost radius 2, with all the other data being close to the data of a sphere of radius 2 Minkowski, and then trying to glue these things in vacuum. In order to do that, if you're sufficiently close to Minkowski, it suffices to look at the linearized equations and do your gluing there, and then use an implicit function theorem to pass to the nonlinear theory. In any case, so you have to first solve the linear problem, the linearized problem, and the infinitely many conservation laws are precisely these expressions here. So you have 4 different types of expressions which are conserved for the linearized equations around Minkowski. And what does that mean? That means that if you take the d derivative, remember that derivative along your null generators, the d derivative of each of these expressions is 0. You don't see integrals here because you can see that I have already projected them at spherical frequencies. This is the one spherical frequency. Okay, this is just a function. This is this guy here again. Denotes another type of spherical projection. Again, spherical projections, spherical frequencies, spherical projections. Okay, so some of them are actually integrals in the sense that you have to project to spherical frequencies. Other of them are not. But you have these 7 types of conservation laws. Okay. Now, all of them are abstractions, okay? So because these guys have their own value at the sphere S2, have their own value at the sphere S1, and these values, unless they are the same, unless they match, you cannot do your gluing. That's the thing. All of them are abstractions to gluing. Dot here over each geometric expression means that I am looking at the linearized component. Sorry, where do you see, sir? The circle, this guy here. This guy means that I'm taking the divergence with respect to the round unit metric, not with respect to the induced or something else. Okay. All right, so how do you now survive given these conservation laws? Okay, so there are 2 things you can do to match your data at to match these conserved quantities from S1 to S2. There are 2 things. You keep S1 as it is, and you change your world as S2. And you try to change your world at S2 so that your new world has values for the conserved charges that match the ones at S1. And so you hope that then you can glue S1 to this new thing at S2. And what are the 2 things you can do? Well, the first one is you keep S2 as it is, but you change the angular coordinates at S2. Okay, so in other words, you consider a diffeomorphism of the sphere. That changes intrinsically your geometry and gives you a new geometry, but at the end of the day, is isometric to the original one. And maybe this new, with respect to these new coordinates, that the geometry here can be matched to or the components of the geometry here can be matched to whatever you need to be matched with S1. The second one, which is more severe and probably more important, is that, okay, if you want to follow linear theory, it will be impossible to match S1 to S2 exactly. Even if you do a spherical diffeomorphism of S2, you will have to perturb S2. Okay, and how do you perturb S2? Well, you have the under construction outgoing, let's say, null surface if you are gluing from a sphere of radius 1 to sphere of radius 2. You have the outgoing null surface, and at S2 you have the incoming one. So you can consider all the local perturbations of S2 at this transversal direction. Okay, transversal relative to the under construction one. And that's what we call a sphere perturbation. Okay, so You allow yourself not to glue exactly at S2, but to glue to some perturbation of S2 along this transversal purple hypersurface. So the combination of those two perturbations, okay, the sphere diffeomorphism and the sphere perturbations, the combination of both of them are enough so that you end up with a section here, a new section, S2 prime, in which, or on which, your data here, sorry, not that your data, these functions here match the values of S1. And that's what you want. If you don't have complete matching of all of these expressions at S1, S2, then you don't have gluing. So by changing S2 to S2 prime, what you gain is that the values of these expressions at S1 now match the values of this expression, not at S2, but S2 prime. That would be amazing if that would be true, but it's not true. Because, okay, these are infinitely many numbers, okay? Because this is a function, like not all of them are projections. Some of them are not projections. This is a function. Conserved charge is a number, right? Some of them are functions, which are represented by infinitely many numbers. And in that sense, I say infinitely many conservation laws. There are 7 expressions, but the level of numbers are infinitely many numbers. So you have infinitely many numbers that are conserved. This procedure is enough to match infinitely many, but 10. These 10 here, okay? These are 10 numbers. This is one number. It's a projection on an integral. It's a spherical mean. That's 3 numbers, 3 numbers, 3 numbers. You let m go 1, 2, 3, or 0 minus 1 plus 1. So 3 numbers, 3 numbers. 3 numbers, 9 plus 1, 10. So these 10 numbers cannot be matched among these, even if you do that local perturbation of your final sphere. All right, so still, let's keep that in mind. So that's the first result we can show. Given a sphere here and another sphere here, close to Minkowski, you can do gluing in a characteristic direction from S1 to a perturbation of your future sphere, to S2 prime. And all your geometry is perfectly, it solves the constraint equations, and everything is continuous from S1 to S2 prime, apart from 10 numbers. 10 numbers will be discontinuous here, because you have not matched them. But it's numbers, 10 numbers, not 10 functions, 10 numbers. That's the first result. It's a codimension 10 perturbative gluing. Okay, perturbative because we don't finish at S2. We finish at the perturbation of S2, and it's codimension 10 because 10 numbers we have missed. Like we have not been able to glue them. And that's the final thing you get from this result. Right? You start from S1 and you construct sections which terminate at the perturbation at S2, where again at that perturbation you fail to match 10 numbers. Now, what if you don't want to perturb S2? You want to start from S1 and finish at S2. Well, you can do that provided, what if you want to drop the perturbative aspect of the previous theorem? You can do that provided you don't just move along one null hypersurface, but you move along 2. So you start at S1, you can go, say, backwards along a null hypersurface. You terminate at the section of it, and then you move along a null hypersurface in the outgoing direction. All right? This is, again, everywhere you move along null hypersurfaces, but it's not just one null hypersurface, it's 2. Okay, and in order to go from one null hypersurface to the other, basically you have to go from an incoming to an outgoing. And you transition at some Bifurcat sphere. And that, if you do that, if you allow yourself to have that break of your null hypersurface, then you don't have to perturb this guy. So this is not perturbative gluing, it's by Furkat null gluing. The codimensional 10 restriction still applies. Okay, when you solve from here downwards and then upwards, you will match all the geometry here, but the numbers. Okay, one idea about how to prove these results. Remember that the free thing that you have to do whatever you can do whatever you want with is the omega, and this is a linearized omega. And the second thing is the conformal geometry. And the conformal geometry somehow it's actually you can even see here the relation, but anyway, it's related very closely to the traceless part of the second fundamental form. So these are basically the two things that you can freely specify. Now, let's try to solve the constraint equations so that you do matching from the one sphere to the other. What does that mean? That means that you look at your geometry at the second sphere, you look at the geometry at your first sphere, and you want to make sure that both of these values are specified, and you still solve the constraint equations. So if I know my conformal factor at sphere 2, and I know it at sphere 1, this is given. Forget about this for a second. And the constraint equation tells you that this guy has to be equal to this. So that immediately tells you that the omega that you have to specify, which as you remember, you can specify freely, has to be such that this integral from 1 to 2 agrees with whatever data you have at 1 and at 2. These are what we call a representation of formulas. It gives you the difference of your geometric terms at the final and the initial sphere in terms of the things that you can freely specify. And what is magic about the null constraint equations, okay, this is the whole core of the proof, is that for most of these differences, right, for most of the things that happen initially and finally, the representation formula involves the freely specified things for the characteristic problem with different weights here. Okay, so it's the 1 over r squared times he that gives you this. It's the 1 times chi that gives you this. It's the 1 over 3 times chi that gives you the other one. So in some sense, you can use orthogonal parts, independent parts of this guy to specify so that different components of the geometry match. Now, what is the enemy? The enemy will be the cases where two different geometric terms rely on the same power of R. When that happens, is exactly the case where you have conservation loss. Okay, and that's where you cannot use the freely specified data to glue. That's the idea. Now, remember, at all places so far, I have said I cannot match 10 numbers. No matter what, 10 numbers. 10 numbers are not matched. How can you match those 10 numbers? Well, you can match them provided that you start from S1 to some S2, and for that S2 lives in a space-time that you have more information. And what is that like more information? For example, if you are in care. Okay, you can assume that S2 is in care, and not any care, but just some care that you have the right to choose. Because that right that you have to choose your care will allow you to match those 10 numbers. Okay, and that gives you a characteristic version of the Corvinus theorem. Right, choosing your care is the final ingredient that will allow you to also match the 10 numbers that you have not been able to match anywhere. And I forgot to say something important is that these are the 10 numbers. Sorry, these are the linear charges. These are the nonlinear charges. And this is related, especially if you look at these integrals asymptotically. This is related to the idea of mass, linear momentum, angular momentum, center of mass. All right, there is another work by Carlotto that has to do with localized gluing, where you don't just glue everything. You don't just cut off your constraints and then you glue them to care, but you keep your data all the way to infinity inside the cone, and outside that cone, after some transition region, you glue to Semikovsky. That's the localized gluing result of Carlotto. And this is a result that you can obtain both in the null and the Riemannian direction using these gluing results. Okay, very quickly, what is purple here? The purple is the transition. Okay, Minkowski is blue. Do I say it somewhere? Yeah, blue is Minkowski. So it's not. This is blue. This is purple. This is yellow. All right. So what you can do is you can start here with your S1. You can have here your S2. Okay, and then S1 is whatever you're given with, whatever you start with. S2 now is what? S2, you can put Minkowski from here to here, like in this region, Minkowski. Here you can keep the original one, and here you have a transition region. And you can use that transition region to match those 10 charges. So now that's full gluing. From something original to something that keeps your original in a cone and gets you to Minkowski outside a transition region. And now once you have that S2, you can play the same game. Going from S1 to S2, you can go from S2 to S3, S3, S4, like that. Okay, you can keep your original metric here. You can keep your Minkowski metric here. And you have the transition region that matches all the charges at every step and all these things. This is, however, very easy to do progressively, precisely because of this transport character of the null constraint. Right? This is so this is much easier to do compared to what you need to do in the Riemannian case. So this is, you do like this sequence of bifurcate, null bifurcate things to get this localized gluing. But then by a basic domain of dependence theorem, you can upgrade this null bifurcate gluing, localized null bifurcate gluing, to an actual Riemannian gluing. Okay, this is, you can choose a Riemannian hypersurface where you are purely original here, purely Minkowski here, and here's your transition region. So going from the null gluing to the Riemannian gluing is immediate, just by a domain of dependence property, as you see here. All right, and I have a few minutes to describe a 7 minutes, 5 minutes, what? Yeah. That's okay. Of course, all of this is you have to go, you cannot go. Yeah, exactly. You want something space-like. It's more or less similar to what you do here, more or less. But of course, you have to do it, as you said, infinitely many times. No, right? From here, which is purely null, you go to something space-like. Thank you. Okay, last application. Again, an application by our friends Christoph and Ryan, who have used this characteristic null gluing to falsify the third black hole thermodynamics law. Yeah, I forgot the law here. Okay, so what does this theorem, what does this law tell you? It tells you that you cannot form regular one-ended extrema black holes from sub-extrema black holes. Okay, somehow you cannot have a mechanism that converts a beautiful regular sub-extrema black hole into and makes it into an extremal black hole under regularity. Okay, without regularity, you can work at more singular models. All right. So what did Ryan and Christoph do? They constructed a space-time which is perfectly regular everywhere regular. It's one-ended, not two-ended. Eventually, it is exactly extremal horizon Nordstrom. So this is an extremal black hole here, extremal horizon Nordstrom black hole, extremal horizon, extremal domain of dependence. But before that extremal black hole, you are in a portion of your event horizon exactly Schwarzschild. So here, as you gravitationally collapse, you form your black hole, you are Schwarzschild, and then there is a mechanism that makes Schwarzschild into extremal horizon Nordstrom. And that's in the context of spherical symmetric Einstein-Maxwell charge scalar field system. All right, the construction of these spacetimes is what it allows them to falsify that law. Now, how do they construct the spacetimes? Well, the most important thing is precisely what happens here, right? Because that's a transition from Schwarzschild to extremal horizon Nordstrom. And as you can see here, this transition is a transition in the null direction. Because after all, we care about going from sub-extremal event horizon to extremal event horizon. So it's really along this null hypersurface where we want things to transition from sub-extremality to extremality. So this is the main construction that they do. Take data that you like here. This is away from Minkowski, by the way. But what saves them is that you're still in spherical symmetry. But it's away from Minkowski. Our result is close to Minkowski. You start with one space-time you like, all right, of this form. You start with another space-time you like, you put it here, and then you do a characteristic gluing along this null hypersurface. Now you can do local existence here, local existence here, so somehow you can connect those two space-times by using this null hypersurface. Okay, that's the main idea. Let's specialize a little bit that idea. Let's start first with Minkowski. Why do we want to start with Minkowski? Because Schwarzschild does not have a beautiful regular center. You have to start with space-time that you know is one-ended and has a beautiful center for some time. And what's better than Minkowski? So you start with your first space-time to be Minkowski because it takes care of all these things here, one-ended center and all these things. And then along one null hypersurface, you do something, you do your null gluing, and you connect it to sub-extreme, to what? You connect it to horizon Nordstrom space-time. I think this could be zero, by the way, but anyway, you allow also extremality here. But the first construction is to go from Minkowski to horizon Nordstrom. All right, that would tell you that you can have a beautiful space-time that does what? That collapses to an potentially extremal black hole if you let that value Q to be 1. Right? So you can have creation from regular data of an extremal black hole. Of course, if you take Q sub-extremal, then you have collapse or creation from beautiful data to a sub-extremal black hole. But the important thing here is again in the extremal limit. So this is gravitational collapse to an extremal black hole construction. Okay. Let's go one further step because that's not what the third law wants, right? The third law wants to start with a sub-extremal black hole and convert it to extremality. It's that transition. That's what the third law wants. Not to go from here to here, but to go from here to here. It's that transition that's not allowed. And that's what's done in the next work of Ryan and Christoph. You have your Minkowski. You glue it nully, in a null way, characteristically, to exact Schwarzschild. So you have now a space-time that has formed a black hole, which is Schwarzschild locally, but I mean the event horizon and the apparent horizon are isometric to the Schwarzschild ones. So in that sense, you can say your black hole is Schwarzschild. And once you have this for some time, then again, you can do your new gluing to an extremal black hole. So by combining those three things, you end up with, and I'm done in 1 minute, you end up with beautiful regular data, one-ended, beautiful center. You collapse to something sub-extremal, which then gets converted to an extremal black hole. Okay, that's their work, which I think is a very nice extension and generalization of the null gluing problem. an application of it. And what is actually the main idea that their work brought or used is that you can actually, and that's the deeper reason why you can form extremal black holes from sub-extreme black holes. In regular spacetimes, the idea is that you can have an apparent horizon which is discontinuous. In regular spacetimes, okay, the singularity of the apparent horizon does not affect the regularity of your spacetime. And in fact, in the irregular spacetimes, their apparent horizon discontinuously jumps backwards. As you go, let me go to the first picture. As you go from Schwarzschild to extremal. This is the event horizon in Schwarzschild. No. This is Schwarzschild, but the actual event horizon of the Schwarzschild is here. But if you look globally for this spacetime, the event horizon is here, but the apparent horizon is here. Okay, hope it makes sense what I'm saying. And anyway, if you follow now this apparent horizon for Schwarzschild, then when you transition to exact extremality, that apparent horizon gets shifted here discontinuously. And that's something that the reconstruction basically allows and actually strongly uses and needs in order to have that transition. So the ingredient, the technical tool, is the null gluing. But the main reason why this construction is allowed is because of this discontinuity of the apparent horizon. Okay, thank you very much.